Hello, guys. Welcome to another episode of CUDA Education. Today, I wanted to make good on my promise of, you know, elaborating more on this indirect commands buffers parameter, right? So if you notice here, the first parameter is the command buffer, and the second parameter is the buffer that we're using to basically you know run the draw commands, right? So how is this buffer built? Where does it come from? What's going on with it? And what's happening with this buffer now. Just if you're curious, notice that we're talking about the tree, or the part of it where we do the multi-draw indirect, right? So we submit the entire buffer, and we do one draw call from the CPU to the GPU, and we submit the entire buffer to the GPU, and then the GPU goes in and just reads what is inside of the buffer. Okay, so it's just one submission here. Okay, one submission here. As I said, not directly the previous, but the previous to the previous video. It's just one submission here. If we if we don't have the multi-draw indirect feature on our GPU, then we have to submit each draw call one by one, right? And as we could see here that is the case. So we have a for loop that's basically going over the size of indirect commands, and it's literally pushing through all of the draw calls basically manually. So there's like 260,000 plus draw calls that are being submitted one by one in this for loop from the CPU, right? And we're not submitting the whole buffer one time. Now now we're basically looping and submitting the draw calls one by one. We have everything enabled here. Instance count is 1. But this is what gives us the CPU stutter that we saw in the previous videos, right? We get the CPU stutter because we're for looping. We're basically issuing 200,000 plus commands from the CPU to the GPU, which is wildly inefficient because you have driver overhead, you have just synchronization issues, memory issues, moving things from one to the other. The CPU and the GPU has to always be communicating. It's very inefficient. Whereas here, if you do just one draw call, and then all the information is baked into the GPU, and the GPU could just read the buffer, read the instructions in the buffer from what's in memory. It's way more efficient. So this is one draw call. This is 200,000 plus draw calls, right? So yes, I promised that I would investigate this guy more, right? And actually, if we go to Nsight Graphics, which is the graphics debugging tool for people with NVIDIA GPUs. So if you have, if you want to join in on the fun and pursue learning computer graphics, I highly recommend that you get an NVIDIA GPU, just because they have the Nsight Graphics tools and the ecosystem and things to really investigate what's going on. So in the Nsight Graphics tool, this is the buffer that's actually being submitted. So notice that we have the draw call. So these are all the draw calls. Notice that we have 260,000 plus draw calls. We have index count, instance count, first index, vertex offset, and first instance. But what I wanted to basically point out here is that this is a lot of draw calls to be for looping between the CPU and the GPU, right? It's a lot of draw calls, right? You don't want that. You want to just submit this data one time to the GPU, or submit one draw call to the GPU, and then the GPU can just go into its local memory and follow instructions, right? You do not want to have to be looping through each one of these things, on the CPU side in a for loop in order to draw each one, right? This is subject to change based on what the cull shader decides. So the draw count is what the cull shader uses to decide whether to actually draw or not. We have investigated that here. Cull shader lives on the GPU. We do a distance test to find out whether the object is within camera space or not. If it's not within camera space, we basically call it out, instance 0. If it is, we display it, instance count 1, right? So that is, I'll actually just run the application again. So as you guys see here, guys, if it's within the camera space, we show it. I'm going to freeze a frustrum, but if it's outside of the camera space, we don't show it, right? If we unfreeze a frustrum, we will show everything again, right? But then if we freeze again, notice that now all of that stuff is gone. All of that stuff is gone. And then we could unfreeze. And that is how the culling happens, right? So the culling happens on the GPU side, where the compute shader, the cull.comp, the compute shader decides, it does a distance test and decides, right? It does a distance test and decides, do we display the object or do we not display the object, right? If we display the object, instance count is 1. If we don't display the object, instance count is 0. So, this buffer and that compute shader is what that compute shader it's what manipulating this instance count thing. So we could see that most things are 0. We're deciding not to show most things, but we do have here instance count of 1. Okay. So yeah, just wanted, for those that maybe didn't follow fully all the other videos, just wanted to get you guys updated on what's going on. All right, but we're gonna have to spend some time on this indirect commands buffers situation, right? So what I like to do is just do okay, so we create an array of buffers, contains the indirect drawing commands, right? And we have indirect commands buffers. We could do a quick define on the buffer thing. Encapsulates access to a Vulkan buffer backed up by device memory. So this buffer is GPU side, right? As we know from here, this is all GPU side. This is on the GPU, right? To be filled by an external source like the Vulkan device. Okay, so whatever, right? So we have an indirect commands buffer that's supposed to be GPU side, all right? The next thing is we have to basically, we have a deconstructor. We did, good housekeeping, guys. Always make sure if you create something, you got to destroy it to free up RAM and all that stuff, right? You don't want stuff to be hanging around that you're not. Okay. All right. So then we have our indirect commands buffers here. But basically it's a staging buffer situation. So you guys, I'm going to repeat it again because I don't want to keep saying the previous video. But if you guys remember, we create a shell structure on the CPU side, right? We create a shell structure on the CPU side that basically mimics the structure on the GPU side, right? So we have indirect commands, which is the CPU side, and indirect commands buffers, which is the GPU side, right? So we mimic, it's almost like identical twins, but one is on the CPU and one is on the GPU, okay? So these identical twins, when we create the identical twin on the CPU, we make sure that the structure is the maximum size that it could possibly be, right? So it's like you're building a warehouse, right? And there's this big balloon that it could be really small or it can be really big, right? So if you're building a warehouse to contain this balloon, you need to know what is the maximum size that the balloon can be, right? When it's inflated, right? What's the maximum size? So that is what this indirect commands buffer thing is. It's basically a shell or structure. It's a shell of, what's the maximum size of the structure, and we're gonna basically build the structure to be that maximum size, and then copy that size and that buffer and all the details, the blueprints, the architectural files, all the information, all the permits, building permits. We're gonna copy it over into the GPU, right? So we have a staging buffer here where we're basically copying it over into the GPU, and we're creating our GPU version, right? So this is our GPU version, and we know that because we have VK memory property device local bit. So that tells us right there when we're creating the buffer that we're talking about GPU local memory, right? We also have a flag called VK buffer usage indirect buffer bit, right? And that is basically allows us to do the indirect draw calls, okay? So in order for us to do the indirect draw calls, we have to have this flag, right? We have to flag this buffer as saying, hey, we're gonna do indirect draw calls on this buffer. So, I'm just telling you that this is gonna be an indirect draw call capable buffer, right? And then we have storage buffer bit, which just means the compute shader can write to it, right? And that makes sense because the compute shader here has to write, it has to say is instance count equal 1 or is instance count equal 0? What is the, what are the details of this? What is first index? What is index count? All that stuff. Remember, guys, first index, index count, all that stuff. This is on the GPU side, right? So the compute shader on the GPU has to be able to write to this buffer. So when we create the CPU version, we do the size of VK indexed indirect command, right? This is what decides. This is what decides. This is what tells us. Right, VK right. So indirect command size, right? So again, we have to basically say, give me the maximum number of draw calls that you could do, right? Give me the maximum number of draw calls that you can do, and give me the maximum, and then multiply that by, of course, VK draw index indirect command. So for each one of those draw calls, how big is it, right? That's basically what that's saying. So indirect commands. There is a multiplication that we do. Where is it? Where is it? Where is it? Come on, guys. Where is it? No, it's further up. Okay. There's an. Right, this guy right here. Right, so we're building out the indirect commands. This is the CPU side version. We're building out the indirect commands, and we're making it the maximum size that it could be, right? So the warehouse has to be the biggest size it could be to host the inflated balloon at its maximum size, right? So that's what so that's what that's what this guy is, right? And then we do a staging buffer operation to basically copy what the CPU side version is over into the GPU side. So indirect commands for the CPU side, indirect commands buffers for the GPU side. Notice here, this is the source, transfer source, transfer destination. I do have a whiteboard video that talks about the staging buffer, right? So this is the source, this is the destination. Notice that we have property host visible and property host coherent for the CPU side, and then for the GPU side, we have different flags, right? Every time you create a buffer, you have to associate flags with it. You have to tell Vulkan and the powers that be, what is the buffer? How do you plan on using it? Who can see it? What commands can be run from it? All of that stuff, right? So we create a GPU side buffer that deals with that deals with that is the maximum size that it could possibly be. So again, let's say the maximum size, the maximum number of draw calls is 262,000, right? We have to make sure that our buffer can contain all of these draw calls, because, for example, all of these could be, we could say, okay, I want to turn on all of these objects, right? So a lot of these objects are turned off, but we could say, okay, I want to draw everything. So if I draw everything, everything is going to be 1, right? If I draw everything, everything is going to be 1. And the warehouse has to be able to contain that. If we inflate the balloon to the maximum size that it's going to be, the warehouse has to be able to hold that that balloon. Okay, so that's what that is about. And then we get to, so let's just continue. So let's just get to, yeah, we'll deal with that later. So you guys know for sure that we have to also, we have to have, there's assets and descriptor sets and stuff. So we have to, bind this indirect draw commands output buffer, right? So we have to bind it. So it's binding, it's bound at location 1, right? This line is very important, right? Because when we get to the compute side, which is on the GPU, we have to be able to access the buffer. Okay, we have to be able to access the buffer, right? We have to be able to access the buffer. So one other thing, let me just, yeah, we have to be able to access the buffer, right? So binding 1, this is how the shader on the GPU is able to access the buffer, right? And to manipulate it basically with what it wants to do. So we have a structure here, and then we have indirect draws. We initialize 1 as indirect draws. And then notice that when we do our distance and our frustrum test, that we're manipulating indirect draws instance count. Indirect draws instance count is 0, right? So we have to be able to now talk, the shader on the GPU, right? The shader on the GPU has to be able to talk to the buffer, right? So this binding is how we are able to link up, basically link up what's going on the what we put over into the GPU to the actual shader, and we do it via binding 1. Notice that this is under prepare compute function. Okay, so this is how we talk to the buffer on the GPU, right? Via binding 1. And then just for good housekeeping and to clean up, clean up the situation, I want to talk about, should I talk about it now? Okay, yeah. I want to talk about when the so we have build graphics command buffer and build compute command buffer, right? So these are the command buffers that we're following. I just want to briefly discuss the fact that if this is a synchronization thing, which is not necessarily relevant to this particular topic, but I just want to touch on it really quick. If you have a GPU where the Q family for graphics and the Q family for compute is not the same Q family, we have to be able to manage. We have to be able to manage the. We have to be able to manage, the separation of the two Q families, right? And because we have to manage the separation of the two, because one Q family deals with graphics side stuff, basically rendering what you see on the screen, and one Q family deals with compute, which is basically deciding whether an object is visible or not, right? Deciding whether an object is visible or not, 0 or 1, right? And deciding whether an object is visible or not, if the position is within the camera, we show it instance count of 1. If it's not, we put it at 0, right? 0 or 1, right? 0, come on, give me 0 or 1, okay? So, in order to deal with the separation of the two, because it's different different Q families and stuff, we have to deal with synchronization, right? So we acquire the barrier. So we basically say, okay, guys, everyone get out the room. I am the only one working here. And we also release the barrier. Okay, guys, I'm done doing my work. I have now released it to the masses, and you guys can further modify it and do whatever you need as you like, right? When I need to work on it again, when I need to do something again, I'm going to acquire back the barrier, right? So you have that for the graphics command buffer, and you have that for the the compute command buffer, right? So we have an acquire again, and we have a release again, right? Now the thing is that my GPU is an RTX series GPU, so we don't necessarily have to worry about graphics and compute separation because it's all one and the same. So it's implicit synchronization, right? I don't, it's either I'm doing this or I'm doing that, right? But it's still the same room, right? And we can only do one thing at a time. So implicitly, it's either I'm working on the thing or I'm not. If I'm not working on the thing, then someone else in the room can work on it. But if it's two separate rooms and each room doesn't really know what's the status of the object we want to work on or the status of what's going on in the other room, then we have to do synchronization and barrier management and stuff like that. This, the fact that you have the separation is going to slow you down, right? Because now you have to deal with synchronization, right? Guys, we're dealing with 262,000 draw calls, okay? We have to decide whether to draw, and we actually have to draw. We have to decide whether to draw, aka compute stuff, and then we have to draw, aka graphic stuff, right? So the two have to, the two have to be done. If you have a GPU where, it's the same set of people doing both in the same room, then you don't have to worry about, there's implicit synchronization and stuff. But if it's two separate rooms and each room can only do one or the other thing, whether it be graphics or compute, then we have to deal with synchronization, because you don't want to try to be working on a thing while the other person is working on the thing. You don't want one room to be working on the thing and the other room to be working. You'll get undefined behavior. You'll get garbage content. Bad things will happen. Okay. So just to sum it up, guys, I don't even know what I'm going to label this video as, because it's so many things that I've covered. But in the description, I'll probably, just try and outline all that I covered. But yeah, so the thing that, the basic thing that I wanted to cover is that the CPU it binds the descriptors, it dispatches the compute, it, inserts the memory barriers if you're dealing with, separate queue families, and it issues the indirect draw call, right? So here, if your GPU is capable, it does one draw call. And then here it does many draw calls. Remember, guys, we had to, the GPU is going to read all of this data in here, which is why in the staging buffer, we have this indirect VK buffer usage indirect buffer bit, right? Because the GPU is going to go through all this data and render what it sees in here. Okay, remember, rendering is ultimately done by the GPU, right? That's why we call GPUs graphics processor units, right? The rendering is done by the GPU, right? But basically, the GPU is just going to dive into this buffer and then follow instructions. So we're drawing this object, we're not drawing this object. These are the index count. This is the first index. There's no vertex offset, and this is the first instance of what we're doing, right? And this is the draw count, right? So the GPU jumps in here, it follows instructions, and that's it. But in order for that to happen, in order for the GPU to jump in the buffer, you have to have this flag, usage indirect buffer bit. All right, guys, and that is the conclusion for this video. So I'll upload this video, guys. Guys, if you want to be able to follow along, you want to learn computer graphics in 2026, make sure you have a Windows-based computer with a Vulkan-capable GPU, preferably an NVIDIA GPU, because we have the Nsight Graphics tool, which shows us all of the it shows us all that's going on behind the scenes, RTX series and above. Tutorial number 1 installs the Vulkan SDK, and tutorial number 13 installs the all of these examples, right? So we have a bunch of examples. If you want to be able to run the ray tracing examples, you need to have a ray tracing capable GPU. The RTX series in NVIDIA is ray tracing capable. Now, what else was I going to say? Yeah, guys, let everyone know, learn some computer graphics in 2026. It's a process. It's not overnight, but it's a good process. If you're on the bus, if you're on the train, if you have a commute where you have some free time, it doesn't hurt for you to listen to these videos and for you to understand what's going on. I try my best to make these videos simple and straightforward, but it's really cool stuff, guys. This indirect stuff, I still have to do some more things, because there's, this application, just the source code is 700 lines plus, right? So I'm probably going to hang around this application a little bit more, talk about a couple other things before moving on to the next example. Indirect and instance pipeline, right? We have to figure out what that's about. All right, guys, thank you for watching CUDA Education tutorial number 1 and tutorial number 13. Have a great day.